Let's talk about fluid pressure. This is only an application of distributed forces. So if you've seen the video before about distributed forces, this is going to be easy. We're going to learn two things. One of them is that when fluids are not moving, the pressure created by these fluids in objects is going to be perpendicular to that surface. And the other one is that the magnitude of that pressure is going to be proportional to the depth of the object or the location where we're trying to calculate that pressure. All right, so let me explain what I mean by that. Let's say that we have a plate in water. So let's make the assumption that this is our water level, and we're gonna see a plate somewhere in here. And by the way, I'm just only drawing the cross section of the plate. So make the assumption that that plate is going perpendicular to the paper, perpendicular to your screen. So there's going to be a depth of that plate. Let's call it that way. What we're going to see is that the pressure at this point over here, when you don't have as much depth, is going to be less than the pressure at this point over here, when you have more depth in the water. Of course, there's going to be a pressure in the other side of the plate, but for now, let's just look at the pressure in this side of the plate. So what's going to happen is we'll have a value of pressure over here, and that's going to start increasing to a larger amount over here, right? So something like this. And then that is going to form our distributed force. Okay? So again, one of the important parts to remember about this is that that distributed force is going to be perpendicular to the surface, right? It's perpendicular to the surface. And the other thing is that the magnitude is a function of the depth, right? So the magnitude function of depth. All right, so those are two important things to remember on that. And let me close my screen so we can use more of the screen. Okay, my camera to use more of the screen. All right, so the value of the pressure is going to be, and remember we're talking about a three-dimensional plate or two-dimensional plate, right? It has a surface. We're only seeing a cross-section of that surface. But that pressure, the value of that pressure is going to be equal to a rho g h, multiplication of rho g and h. Let me explain each of them. This h is the depth. So for example, for this first number, this is going to be, let's say, my h1, right? It's going to be my h1 over here, right? The depth of that particular point, right? Over here, when it's deeper, it's going to be my h2. So I'm going to have more pressure in that because of the h2 is larger than h1. G is my gravity, or acceleration due to gravity, right? And just as a reminder, if we're looking at the International System of Units, this is 9.81 meters per second. And then we have 32.2, and this is second square feet, second square, okay. And finally, what we have in this rho is the density of the fluid. In most cases, we're going to be looking in civil engineering is water, not always, but in most cases we're going to be looking with water, especially when we're looking at water resources. So I'm going to tell you about water. We have that this is 1,000 kilograms per cubic meter, or about 62.4 pounds per cubic feet. So those are the values that we have. And once again, remember, one of the assumptions that we have is that the fluid is actually not moving. Once the fluid starts moving, things change quite a bit. So that's it. That is basically the concepts that we need to know to be able to deal with fluid pressure in statics. Just remember that the distributed force is perpendicular to that surface, and that the magnitude is given by the equation that is right there on the right hand side.